Okay, let's look at the synthesis of the heptagon. So what is our given? So we're going to be given a segment, and the idea then is to construct a regular heptagon with that segment being the side of the heptagon. So let AB be our given segment. So what do? Well, first we construct a perpendicular to AB, let's call it BG, such that AB is equal to BG, and then we're going to extend BG to some H out here. Then we're going to put in our conic sections. So we construct a parabola with vertex A and axis AB and parameter AB. So that's going to kind of look like that. That's our parabola. And then we construct our hyperbola with vertex B, axis BH, and parameters AB, both parameters equal to AB. So again, we get a hyperbola. And let T be the intersection of the hyperbola with the parabola. The intersection below BH right there. Okay, so then what are we going to do? We're going to extend AB. We're going to construct a rectangle here. So we extend AB to Z. Here's our rectangle here. And then we have our rectangle here. Let's call that E. Okay, and next we're going to extend G to D such that GD is equal to BZ. Okay, and so then we have a divided line segment EBGD satisfying DB times BG equals BE squared, and GE times EB equals GD squared. Okay, and that follows directly from the symptoms of the hyperbola and the parabola, and the fact that AB and AB or BG is the only parameter that's around there. Okay, just pause here. And okay, so what I've done is I've just scrubbed out the hyperbola and the parabola. And so we've got our line segment EBGD, and I turn that into a triangle. So I just get my compass at the point B, and I do a circle of radius BE, and then I put my compass at G and look at a circle of radius GD, and where those two radiuses intersect, I'm going to call that the point I. So it's different from the A that was in the previous slide, which we used to construct the hyperbola and the parabola. Okay, so we've got a whole bunch of isosceles triangles. So let's these angles be X and these angles be Y, right? And so what happens next is that because of the relation dB times BG equals BE squared and GE equals EB equals GD squared, then we can prove that the triangles IBG is similar to the triangle DBI, and the triangle IEB is similar to the triangle GEI. So that means when we go ahead and do that, that means the angle BIG is equal to the angle GDI. So that means this is also a Y. and EIB is equal to BGI. So this is an X right here. So that means we have shown that the triangle EID and the triangle BIG are these 4-2-1 triangles. Okay. We go to our next thing. So I'm going to just pause. Okay, and so we take our triangle BIG, which is a 4-2-1 triangle, and so we circumscribe a circle around it. And so then by Euclid Book 6, Proposition 33, BG is 1/7 of a circle. So BG is the side of the regular heptagon, and remember BG was equal to AB. So so that's the side of our desired heptagon, and so then we just complete the heptagon by just taking that side, taking that length, and just sort of completing out the heptagon. Okay.